if you've got a curve, what's an osculating circle? Now I was going to start with something else, but since you asked, that's where we're going to start. Okay, you got a curve here. Okay, and this curve is drawn in a plane, but it could represent a curve in space. Okay, and the osculating circle, well, in this case, the osculating circle, let's draw one right at this point, okay? It's the circle, osculating, that's a pretty good circle. Yeah, it's one of the better ones I've ever drawn, okay? So apparently I was thinking about the kissing circle, because that's what osculating means. And apparently that stimulated me to draw a really good circle. I have no idea why. Okay, so here's a circle, okay? The osculating circle at point P. So we'll call this point here P. Okay? Okay, it's parallel to the curve at the point P. With the same curvature. Okay, in other words, the curvature of this circle is the same as the curvature of the curve.
Okay.
Okay? Know how to calculate the curvature of a curve? Did it in calculus 2. It's basically how quickly the
Wouldn't that be the second derivative?
direction of the curve is changing as you move along the curve. But you got to be careful about what parameter you use to move along the curve. So we're going to define it in a minute.
I think that was Calc 1.
Actually, yeah, you can do it in Calc 1. Because it's just basically the second derivative divided by the first derivative. Okay? But we'll see. We'll be specific. Okay, so anyhow, that's what an osculating curve is. Before we get into the definition of curvature, which is really fairly straightforward, but there's one formula that's a little bit challenging. Okay? Before we develop the topic of curvature and the formulas and so forth, we want to specify one important concept of this, or one important aspect of this. This curve could be in 3 dimensions. Okay? So that the osculating circle has to be in the same plane as the motion along the curve, which I'm saying in kind of a fuzzy manner, because we haven't defined the unit tangent, unit normal, and unit binormal. Okay? But as you're moving along a curve, there's a coordinate system that moves with you, with this in the direction of motion, this in the direction in which the direction of your acceleration, perpendicular to that, and this one being the cross product. So you're kind of moving along like this. That won't make a whole lot of sense, but that's kind of something you can keep in mind as we talk about the unit tangent, unit normal, which are fairly simple, and then the binormal, which is just a cross product. If you're flying an airplane and you're making a turn in this direction, well, you're looking straight ahead as you turn, right? So that's your unit tangent vector gives you the direction in which you're looking. You're also accelerating. Of course, that acceleration combined with how fast you're moving tells you what your curvature is. Okay? And your acceleration is partly in the direction of your motion. You might be speeding up or slowing down, but you have the centripetal acceleration. It's a centripetal component that tells you, along with that, your speed, tells you your curvature. Okay, that modifies what I just said. I didn't specify it was centripetal acceleration. So you have your direction of motion and the direction of your centripetal acceleration. Take their cross product and you get this thing called the binormal, okay, which is perpendicular to the plane in which you're temporarily moving, not the airplane, but the plane. So if I'm moving in this direction, centripetal acceleration in this direction, then I'm temporarily in this plane, and that's the way it feels. If I'm looking at the, my airplane is in that plane, my wings and so forth and fuselage are all in that plane, or parallel to that plane, then I can tell how the Earth is tilting and all kinds of other things, okay? Not all kinds, but several other parameters. And if you haven't flown an airplane, I certainly haven't, you don't necessarily relate to those parameters when I mentioned them, if I knew what to mention, azimuth, angles, and all that stuff. Okay. Then, of course, you have the vector that defines the plane that you're in. These two vectors define it, but the one vector that defines it is your binormal, the cross product of these two, which is normal to the plane that you're in, right? And it's easy to calculate those. Tedious in many cases, but easy. Okay? So that's kind of where we're going. So to get an osculating circle, since that's what you brought up first, we have to do all that, right? We have to figure out what plane you're in so we can figure out, well, it's got, so we know what plane to put the circle in, right? And then we've got to figure out your direction of centripetal acceleration equivalently, right? The component of your acceleration or your second derivative perpendicular to your first derivative, your direction, your velocity vector, okay? So we've got to do all that, so that's what we're going to do. Okay?